Have you ever stopped to think about how computers actually think? Or how you can build an argument that's practically bulletproof? Well, it turns out the secret to both lies in the same place, a powerful system called propositional logic. And today, we're going to break down this language that secretly runs our world. So let's start with a really basic question. How does a computer, which is really just a bunch of switches, know what a word like "and" even means? It feels like it should be complicated, right? But the answer is surprisingly simple, and it's all built on a foundation of pure, undeniable logic. By the time we're done here, you'll get it completely.
Okay, so where do we start? Well, just like any language is built out of letters, logic is built out of something even more basic. You can think of them as the atoms of logic, and they're called propositions.
Now, here's the deal with propositions, and this is super important. They have to be a statement that is either 100% true or 100% false. There is absolutely no gray area. No maybe, no kind of. It's a binary yes or no world. And this slide lays it out perfectly. On the left, you've got clear propositions. Washington, D.C. is the capital of the USA. Yep, that's true. 1 + 1 = 2. Also true. But look at the right side. What time is it? That's a question, not a statement. Read this carefully. That's a command. And my favorite, x + 1 = 2. Is that true or false? Well, we don't know. It depends on what x is. So until we know x, it's not a proposition. It has to be a solid, verifiable fact. So we have our logical atoms, these true or false propositions. But atoms are kind of boring on their own, right? We need a way to connect them to build bigger ideas. And that's where logical connectives come in. They're like the glue that lets us form logical words.
Let's start with the simplest one on the block, negation, or just not. It does exactly what you think it does. It takes a true statement and makes it false, or takes a false statement and makes it true. It just flips it on its head.
And this little chart here, this is called a truth table, and it's going to be our best friend. It's a super simple way to see every possible outcome. For negation, you can see if our proposition P is true, then not P is false. And if P is false, not P is true. Simple as that.
All right, now for the one we asked about at the very beginning, conjunction, which we all know as and. This connects two propositions, P and Q. And here's the rule. For the whole statement to be true, both P and Q have to be true, no exceptions. So for that example on the screen to be true, Rebecca's PC has to have enough disk space and a fast enough processor. One or the other isn't good enough.
And the truth table for and makes this crystal clear. Just look down that final column. There is only one single case where the outcome is true, and that's when both P and Q are true. If even one of them is false, the whole thing comes crashing down. This is it. This is how a computer knows what and means.
Now, if and is the strict one, its sibling, disjunction, or, is way more relaxed. The statement P or Q is true if P is true, or if Q is true, or even if they're both true. That's why we call it an inclusive or. It's happy as long as at least one thing is true.
And you can totally see that in its truth table. It's almost the exact opposite of the and table, right? The only way for an or statement to be false is if both parts are false. Any other time, it's true.
Okay, so we've got our atoms and our basic words. Now it's time to build full sentences. This is where we start creating actual arguments and showing relationships between ideas, and we do it with something called a conditional statement. This is the classic if-then structure. If P happens, then Q will happen. Now, this is the one that can feel a little weird at first. Think of it like a promise. The only time this statement is considered false is when the if part is true, but the then part doesn't happen. That's a broken promise. In every other case, the promise is technically still intact.
Okay, this is really cool. From that one if-then statement, you can create these variations. The converse just flips it around. The inverse negates both parts. But check out that last one, the contrapositive. If the home team does not win, then it is not raining. Now, here is the magic trick. The contrapositive is the only one here that is logically identical to the original statement. They mean the exact same thing. And that is a total superpower in arguments, because sometimes it's way easier to prove the contrapositive.
So all these abstract rules, why do we care? What's the point? Well, this is the point. This is how we take messy human language and make it perfectly clear. And more importantly, it's exactly how computers work. Let's make that connection right now. And there it is, the big aha moment. In logic, we have true and false. Inside a computer, we have electrical circuits that are either on or off. We represent on with a 1 and off with a 0. It's a perfect match. True is 1, false is 0. That's the whole secret. So what computers do is they take these long strings of ones and zeros, they line them up, and they apply our logic rules, like and, to each pair of digits all the way down the line. It's just doing that simple truth-false calculation we saw in the truth table, but it's doing it millions or billions of times every single second. That's what computing is at its core. And for us humans, this gives us the power of absolute clarity. We can take a complicated, kind of confusing English sentence, like the one about the roller coaster, and we can translate it into a perfectly precise logical statement. All the ambiguity is just gone, and that's exactly what you need when you're writing code or drafting a contract. All right, for our final piece of the puzzle, let's talk about the ultimate skill in this language. It's the ability to prove that two statements that look completely different on the surface actually mean the exact same thing. This is called logical equivalence. So what does it mean for two statements to be equivalent? It means that if you were to build a truth table for each of them, that final answer column would be identical. No matter what you plug in for the variables, the results always match. They are, for all intents and purposes, the same. Now, instead of building a giant truth table every time, you can use established laws of logic, things like De Morgan's law, to transform a statement step by step. Now, you don't need to get lost in the weeds of this specific proof. The big idea is that this is like algebra. You're just following a set of proven rules to show that this really complicated-looking thing on top is actually just a disguised version of the much simpler thing at the bottom. And that, right there, is the whole ballgame. This ability to prove equivalence is what lets a programmer swap out a clunky piece of code for a much faster one that does the exact same thing. It's what lets an engineer simplify a complex circuit design. It's even what lets you win a debate by showing someone that their complicated argument is logically the same as something obviously ridiculous. So there you have it, from simple true-false atoms to connectives like and or to the rules of equivalence. You now know the language that tells a computer what to do. The only question left is, now that you know the rules for a solid argument, how many flawed ones are you going to start spotting all around you? Thanks for tuning in.